Yep.
I think to check if the screen sharing works.
Sure. Let me know if you can see it.
Not yet.
Okay. Does this work?
Wait.
Sorry.
Okay. Nice.
Okay. So I can just do this, right? Like, I guess just. Try that. Okay. How's the typing?
Let me show you the typhoon. It's like crazy. It's all running outside.
Oh wow.
Just the beginning, yeah.
Yeah. It's meant to get worse tonight, or?
Yes. And okay. Yeah, it's supposed to be the worst tonight, and but it's still very bad at the day. So the Taipei city government, they announced the work cancellation.
Yeah, for tomorrow as well, or not sure yet.
Not sure for tomorrow.
Okay.
Typhoon is pretty unpredictable.
Yeah, I remember. Yeah. Okay. I've been in Kaohsiung now 5 months. I think there was only one time where they cancelled work because of the typhoon. But then actually the day it didn't come, so it was nothing in the end. So I haven't really had a big one, a big typhoon here.
I see. Wow. So, okay, Charlie, are we live yet? No. Okay, now. 3 seconds. Okay. Hi everyone on the live stream. So we are glad to have Ben Devlin to introduce block acceleration using FPGAs. Due to yeah. Okay. I think we are live.
Okay. Should I just go for it? You can hear me okay and see the screen?
Oh, sorry. Sorry. Yeah. I hear. Yeah. So I think yeah.
Yep.
So for everyone watching the live stream, feel free to ask any question in the chat box, and I will reply to you. And so yeah, I think let's get started.
Okay. Yeah, and you can see my screen okay now.
Yeah.
Okay. Cool. Yeah. Thanks for letting me present this. So what I wanted to talk about today was blockchain acceleration, and there's a couple of areas that we looked at on FPGAs. So it's first on, we talk about Equihash, next is kind of elliptic curves, zk-SNARKs, and at the end a little bit on VDFs. And if you have any questions, also feel free to ask as I go through this. So this is just a outline of the presentation that I want to do. So first, just the introduction. I just have a slide on who I am, and then also talking about FPGAs in case people aren't so familiar with them. And then next is the FPGA acceleration project that we did for Zcash. And this was split into three main areas. So first we looked at Equihash. Next we looked at kind of transparent transactions. And I'll talk more about what these are later. But it came down to elliptic curve cryptography on a curve. And then we finally went into zk-SNARKs, which is kind of the special advantage that Zcash provides, which are very private shielded transactions. And we looked at what kind of logic needs to be implemented, and this again was elliptic curve cryptography. Finally, some future direction, and I have an overview of VDFs and how these kind of relate back to FPGAs, and conclusions and acknowledgements. But just quickly about me, who I am. I'm originally from New Zealand, and I studied computer systems. Then after I moved to Japan, where I focused more on electronics, and I did my PhD there in EE, and we did asynchronous circuit designs. We were kind of thinking of new FPGA architectures, and we also touched on RSA acceleration, which is another type of cryptography. And then after that, I moved to America, and I've been working first at Xilinx in the research group for FPGA architectures. And then after that, I moved to New York, and I've been working in finance for FPGAs. But because of changing jobs, I had a 1-year non-compete period where I wasn't allowed to work, and so I got in touch with Zcash, and we worked out this project for taking their blockchain and having some FPGA acceleration. Now I have some slides on introducing what's an FPGA and what are they good for, and this kind of thing, in case people don't know. So the field programmable part of an FPGA, this is kind of saying that it's an integrated circuit, but once you put it out into the field, you can actually still change what it does. And this is opposed to something like an application-specific integrated circuit, an ASIC, where once you've made a chip and you've sent it out and the customer has it, it's actually, you can't really change it. You're kind of fixed in the application. And so because of this, FPGAs are actually really widely used, but traditionally they haven't been so consumer visible. So you might see, an FPGA is probably in your car, or in a 4K television, or even in the latest graphics cards, but they won't be branded as having an FPGA, so not so wide known possibly. And traditionally FPGAs have not been really easy to access. You kind of needed some technical knowledge, or you might need to buy some special hardware. But recently FPGAs have become more and more available. So for example, now on Amazon you can rent in the cloud an FPGA. And this is only a couple of dollars an hour to get very cutting edge technology. So you can do this. You also don't need any. You can also go the route where you use high level synthesis or a software development kit kind of driven flow. And this is where you don't actually need to use any of the hardware level description language to program an FPGA. You can actually program it in C++, and then the tool will put something on FPGA. And so the combination of these things recently is kind of making FPGAs become a lot more popular recently, especially to software guys who want to get some speed up on some application, but might not necessarily have an electronics background. So this is just showing an example of different use cases. So, car technology uses these, a lot of space applications use these, as well as kind of medical instruments. And this is showing what an FPGA is. At the basic level, an FPGA is just a lot of logic gates, routing interconnects, and configuration memory. And typically you would write it in a hardware description language, so System Verilog or VHDL. And then what happens is it's compiled. So it's similar to a software flow where you compile your binary, but instead of mapping to CPU instructions, what we're doing is taking our logic, mapping it to very basic logic gates like an AND gate or an OR gate, these kind of functions, and then place and route. So we try and find somewhere on the FPGA that can fit this logic, and we put it, and then we end up with a chip image, which is a bit stream. And this can be used to actually configure a real FPGA. And while the synthesis, place and route might take 2, 3, 4 hours, once you have this, then in a matter of minutes, you can program the FPGA. Traditionally, they've been a lot smaller, but you'll see recently FPGAs are getting really large, so they can implement huge logics. So now we have 9 million logic cells, thousands of IOs, hundreds of megabytes of on-chip RAM, billions of transistors. The other advantage that you get kind of by going to an FPGA is that you get access to very advanced technology without having to pay a lot of capital. So if you wanted to make an ASIC in this technology, it's going to cost a lot more, millions of dollars, but you can also use an FPGA, which is already 16 nanometer, the latest generation. 7 nanometer is coming out now as well. And so this, for dollars per hour. And this picture here is showing what a basic view of an FPGA looks like. So you here have in the middle these logic blocks I talked about, which will have your function. On the output, you have all of these wires, which are programmable. And then you have these IO blocks on the outside where you connect your inputs and outputs. Yeah, you can see here on the outside. And so new FPGAs also will now have kind of hard logic. So they'll have digital signal processors, so we can use these for high performance multiplying. They'll have a hardened CPU core, even things like next generation PCIe Gen 4 or artificial intelligence engines. So FPGAs are really becoming a lot more powerful and have a lot more use cases as time goes on. And then this is showing what an FPGA looks like inside. So when we make something on the FPGA, we're basically connecting these lookup tables, which have some kind of function. For example, we might say A plus B. And then we would just use more of these lookup tables for a larger input. On the output, we will have some flip-flops or registers where we store the data. And then we also might have some dedicated hardware. For example, if we're doing an addition, the carry chain is going to dominate our performance. So rather than using our routing for our carry chain, we have some dedicated hardware. And when we implement the circuit, you'll see, here's an example. We have a signal coming into our logic block. We have it going into a flip-flop. Then it comes out, it goes through some programmable. So this is what we've programmed. Some switching matrices, comes back to a flip-flop. And the performance that we'll get on an FPGA will actually be determined by how fast the signal is. And then depending on whatever our worst case signal is, and the whole FPGA is kind of limiting what, the clock speed we can run this at. And what I kind of wanted to point out here is that on a modern CPU, you might have 3 gigahertz plus, but on an FPGA, maybe the clock frequency can support 600, 700 megahertz. Because of your logic, you'll often see, hundreds of megahertz. So when you're accelerating something on an FPGA, it's great that you have this, programmable hardware and you can put whatever you want on it. But there are the disadvantages that, well, now we've got a much slower clock frequency, compared to a modern CPU. So FPGA acceleration is ideal for tasks that can be parallelized. For example, you might have a CPU with 8 cores, but on an FPGA, because you can implement whatever you can program pretty much, you can implement 1,000 modules all in parallel. Other things that they're really good for is like custom logic. So on a CPU, you might have an instruction for a 64-bit multiply, but say in our case, we want 381-bit. So we can actually implement this directly on the FPGA, but on a CPU, you would have to do multiple instructions. something that's not memory bandwidth bound is often usually good. So even though FPGAs have hundreds of megabits on board, and you can get DDR or HBM memory if you need it, but when you start accessing this, you actually take quite a big latency hit. So it's ideal if you don't have to do this. And the other thing is, if you have something that has to do a lot of communication with the CPU, it might not be suited, because as soon as you go outside the FPGA, now you're talking, USB or Ethernet or PCIe, and this can be hundreds to thousands of nanoseconds, which can hit your performance. So this is kind of showing an example, right? We have an ASIC on the right, which is very power efficient and very high performance, and a CPU here, which is very flexible but not as powerful, and the FPGA is kind of in between. So it's great for these blockchain kind of acceleration projects where we might have things that are changing, and we want to just try it out and get some good performance. So what we were focused on is this acceleration project for Zcash, and we wanted to look at the blockchain overall and try and accelerate different areas. We didn't want to improve the mining, so we weren't going to make it a miner. So we wanted to kind of improve the verification side of things. We wanted to have open source code, that the wider community could take advantage of and use that doesn't currently exist, and also research, what things work and what things don't. So the three main goals we came up with is Equihash is the proof of work for the Zcash's blockchain. So we wanted to provide, verification for this. Next, we wanted to go into transparent transactions, which are very similar to the transactions in Bitcoin, and this involved elliptic curve cryptography on a specific curve. So we've implemented this, and then we wanted to look at zk-SNARKs, which are the way that they have very private transactions on the blockchain, and these use a different types of operations, but a lot of the big ones are on the specific curve. And then there are also the specific operation for verifications. So we looked at accelerating this. And this is a top level of the design that we came up with in the end. So you'll see in software we have, this can be a user running on their desktop with the Zcash D client, or it can be us running some test programs on AWS. We have some interface, which could be C++ or Python, and this abstracts the access to the FPGA away from the software, so that if you're writing something in software, you don't need to deal with the lower level FPGA details. And then we kind of developed with two mindsets for the interface. One is PCIe, which is for AWS, or if you have a board at home and you're doing all kind of debugging or experiments, we have USB UART. And so we have a kind of message-based protocol between FPGA and software. And this is just an example here. So we have a common kind of header, which is a command and a length. And then after this, we have a custom message depending on what we want to do. So here is a reply to an Equihash verification. And we'll see, okay, did we fail and what's the index and this kind of thing. And so we have a control unit on the FPGA, which is required for every build. But then every kind of acceleration target we added, we made it optional so that you can enable these or disable these, and the whole system will still work. So software will say, hey, what do you have enabled? Do you have Equihash? And if you have Equihash, then we are allowed to talk with them. And this is basically so that when we're creating the FPGA image, maybe you don't need this, and it actually helps the runtime when we're doing our compiling. Or maybe you want to try get a higher frequency, and just having one kind of improves this frequency. This slide kind of talks about the architecture we use inside the FPGA. So we tried to use FPGA System Verilog interfaces where possible. And the reason for this is that it allowed us to design the FPGA to have back pressure. So sometimes when you design the FPGA, you have a clock cycle count, and you know how many clock cycles before something comes out. But then as the system gets more and more complicated, and you have multiple things in parallel, this can be quite complex. So using this kind of interfaces where we have a receiver ready and a valid signal, it actually allows us to kind of plug and play different blocks. So for example, we want to put a really high performance multiplier on the FPGA, we can just plug and play. And because as long as it works with this interface, then it's no problem. And it's very similar to XC-Stream kind of interface. The other point is that you'll see in the design, we have a lot of different equations that need to be calculated, but we don't want to have a multiplication unit per block. So we have these resource arbiters, which kind of share on our interfaces and allow us to have maybe one common multiplier block, which many different other blocks can share. And then this has, you can optionally pipeline or have other functions. So here is just showing a kind of a flow where we have a start of packet for our data, we have an end of packet. If our downstream block for some reason is busy doing something, it can deassert the ready. And when we do this, the source will hold the valid, or it will hold our data. And this is kind of how we have back pressure in the system. And a valid cycle is just when we have ready and valid high in the same clock. And this is also showing, so later on in the FPGA, we need to be able to send really big size pieces of data. So when we're dealing with extension fields, for example, when we do a pairing operation on the BLS curve, we actually have, for example, this here is showing a FP6 packet where we have 6 coefficients, right? And we don't want to have one big wide bus. So what we do is we kind of stack the coefficients. So for example, if we're doing an addition of 2 elements, this is the first coefficients of A and B, and we send it this way. And this also lets us kind of make the design very scalable. So you could have different size extension fields or different curves, and you don't blow up the resources on the FPGA. This is showing the resource arbiter that I mentioned. And what we use this a lot for is to kind of share access to a single resource. So you'll see here we have multiple interfaces coming in, and these will actually, internally they have a bunch of different signals, kind of that I showed before. We have data, control signal, start of packet, end of packet. What our resource arbiter does is it can either be programmed to be priority mode or round robin. So it'll pick from one of the packets coming in, depending on this programming. When it takes a packet, it actually marks the index of where it came from onto the control. And this is so that on the output, so say we have this packet coming through, on the output we can remove the control and put it back on the correct interface. And this way we can have multiple source elements and just one kind of consumer. And then also if we want to have optional pipelining, this is also enabled. And this is to improve our critical delay or to make the clock cycle faster, right? But the disadvantage is we add latency, 1 clock cycle latency. But we can pretty much put this block anywhere in the FPGA, and it allows us for a very kind of modular design. So the first project we did was Equihash. So Equihash is the proof of work that Zcash uses in their blockchain, and it's a generalization of the birthday problem. And what we're basically doing is finding a lot of colliding hash values. And it has a couple of parameters, so you can adjust this. And by changing N and K, you actually change the algorithm memory and time requirements. So for example, Zcash uses 209. And what you need to do is you take the block header, you generate a bunch of hashes. So for example, in this case, we're generating 2 to the power of 20 hashes. And this is where the memory kind of comes into play because you need to store this memory. And then we sort through this and we find our collisions in the hashes. And originally this proof of work was selected because it was thought to be ASIC resistant. And then the reason for this is that, say you need a lot of memory to solve the problem, and memory is generally not cheap, right? And if you have some off-chip memory, then it kind of impacts performance. So this is a good way to make sure that ASICs don't get a huge advantage over CPUs. But then a bunch of ASICs have come out kind of disproving this. So it's not really ASIC resistant anymore. So there has been a plan to move the parameters, which would then require more hashes, and all of the ASICs, in theory, would not be able to adapt as quickly because they're hard-coded. And so what you're doing is taking these hashes, you're XORing them and trying to find a specific subset that equals 0, as well as some index ordering and duplicate restrictions. And finally, you run the block header through a SHA-256 to check that it matches the difficulty. But instead of accelerating finding the solution, what we wanted to do was checking the solution, which is not as intense, but still requires quite a bit of logic. So what we wanted to do is have a FPGA that can take a solution list and produce the hashes, and then check that the XORs match. We also have to check that a certain ordering is followed. So when we're XORing the hashes, the zeros need to appear at certain spots in the tree. We make sure there's no duplicates, and our final difficulty passes. So this is good for an FPGA because it's got a bunch of checks we can parallelize. And when we think about the blocks we need is, okay, we need to implement hashing, and Zcash uses the Blake 2B algorithm. We need a hash map on the FPGA to check for collisions, for duplicates. SHA-256 is the hash from Bitcoin, and this is the one for difficulty. And finally, some control logic. So this is a top level view of the Equihash engine and the way we designed it. So we have an input stream coming in, which is our messages I showed before, and a result going out. And then internally we have a 64-bit bus, and we split it into parallel into 3 different streams as it comes in. The other thing on the FPGA is that you can have logic and you can make it work at different frequencies, clock frequencies, so that, for example, 300 megahertz is faster, right, than 200. And as long as you take care of the clock crossing, this will all work on the FPGA. So we've done that in a few spots. So for our duplicate checker, we implemented a basic hash map, which uses CRC as the hash function. So it's very small overhead. And then this points into a level 1 collision RAM. And if we find we collide with an existing value, then we go into a linked list. And this lets us go through and check, okay, do we have any duplicates in our solution? Difficulty, we just implemented SHA using a core where we pipeline it once and we don't have any pipeline unrolling. So it's a little bit slower, but because we only do this once, we didn't need to make it so fast. And finally, and this is the part we focused on accelerating, is the XOR check. And this is Blake 2B. And so what we can actually take advantage of here is that a lot of the input values are not changing in every hash that we do. It's just the solution index that changes. And so because of this, we actually pipeline unrolled the hash, and it goes through 2 rounds. So these are fully unrolled. And then what this means is that when we send some data in to generate a hash, it takes so many clock cycles to come out, right? So this is 64 clock cycles. But because every clock cycle, every stage is pipelined, it means after the next clock cycle, we get a result. So we take 64 clocks for a latency hit, but then the throughput is every clock cycle, a new result. So it's quite high performance hashing. So we took this and put it on the FPGA, and these are the results just for this one. So you'll see we got quite a big speed up when we compared it to the Zcash decode, just using cycle counters. So 207x speed up. And a lot of this is because of the parallelism and the Blake 2B way that we unrolled it. You'll see the FPGA, it doesn't use too much, it's only a couple of percent. And then you can see here the different clock cycles things take, but then the dominant one is where we're getting 207,000 ops per second compared to the CPU where it was close to 1,000. So that was kind of the first part of the project and a little bit smaller. The rest of the project was focused on elliptic curve cryptography. and we have two different curves. I just have a bit of an explanation about elliptic curve cryptography, in case people aren't familiar with it. So it's an approach to public key cryptography, first proposed in 1985, using elliptic curves over finite fields. And the idea is that you have two keys. So you have a public and a private key. And the public key is a point on the curve, right? And the private key will be an integer scalar multiplied by a generator or a base point, which is everyone uses the same G. And it relies on the fact that it's very easy to calculate Q if you know X and G. But if you only know Q and G, it's very hard to find X. So similar to RSA, where they have the exponentiation problem. But the advantage to RSA is that for the same kind of key size, you get a much smaller key, a much smaller amount of data that you need to store for the same security level. So for example, 2048 bits on RSA is equivalent to something like 224 bits on SEC. So for an application on the blockchain where you want to store signatures of messages or people's public keys, this helps a lot. It's nearly an order of magnitude smaller. And this is just showing different forms of elliptic curves when you change parameters. And so when we operate on elliptic curves, we actually operate over a modular field, right? So, and there's two main ones. The one is over a prime field. So we have a prime value, and then it means any kind of additions, multiplications, it's all modulo prime, FP. The other kind is over a binary field. And the advantage of a binary field to a prime field is that all of your logic now, like adding and multiplication, is using ORs or this kind of compressing, and you don't have a carry chain that you need to propagate. So you can get a lot higher performance when you put it on hardware, but it's not as well studied and possibly not as secure. And so in this project, both of the fields we've looked at are prime fields. And also this picture of a curve here is what an elliptic curve might look like, but when we actually take it over a prime field, you'll see it becomes a jumble of dots. So this is actually what we operate on when we do our ECC. And the first one that we wanted to look at was our ECDSA. And so while RSA relies on modular exponentiation, which can be repeated multiplications and squarings, ECC relies on point multiplications. And the way we do this is by repeated point doubling and additions. So it's kind of similar in a way. And so here on the right is kind of showing a hierarchy of what we need to put on the FPGA. So at the top we have our ECC, and the algorithm we're doing is ECDSA, which is a digital signature algorithm. We have point multiplication underneath this guy, and inside this we need to implement point adding and point doubling. And then at the base level, we're just implementing, addition, subtraction, multiplication, and inversion over FP. And the ECDSA algorithm is what allows us to securely sign, for example, a hash of a message. And this is what gets used in our transparent transactions, so in Zcash or Bitcoin, when someone is authorizing the spend of something. And the algorithm is pretty basic. So this is what we need to calculate. So we do some inversions, some multiplications, and then this is the elliptical curve point multiplications here. And so I talked about point doubling and point adding. And this is an example of the algorithm when we do point multiplication. So what we'll do, it's very similar to RSA, where we take the binary form of the scalar and we say, okay, is it 0 or 1? And then depending on the value of that binary bit, we either do a point add and a double or just a point double. And then we will loop through every bit in our integer. So for example, when we're doing our Secp256k1 curve, which is 256 bits, this is a loop of 256 iterations. And point doubling and adding, how it works on elliptic curves is that point adding is where you have your 2 points you want to add. You draw a line through the points where it hits the curve at a third point is the negative of the result. So we do an inversion, and then this is the actual result. Point doubling is you have a point that you want to double, so we take a tangent. Where it hits the curve, we invert, and that's the result. And this here is just showing that we also have a point at infinity. So when the resulting line doesn't hit the curve, this is our point at infinity. And the actual equations for calculating these are a little bit more advanced, and they involve divisions. So something we also do on the FPGA to avoid these divisions and inversions is we use a projective coordinate system, so Jacobian coordinates. And we represent our x and y point with x, y, and z, and this prevents us having to do as many divisions. So this is the first curve that we looked at, Secp256k1. This was originally used by Bitcoin, but Zcash also uses it for their transparent transaction signatures. So if you're sending Zcash to someone and you're not using their privacy zk-SNARKs option, and this is the one that it uses. And whenever you sign a message, you do it with this using this curve. So everyone who's verifying the blockchain also needs to verify that you had the correct signature that matches. And so this is the curve, and a couple of features of this curve of why it was picked and why is it kind of friendly for hardware. So the first one is that the prime value can be represented by a small number of powers of 2. And so because of this, when we're doing our arithmetic, so for example, addition or multiplication, we can actually take the modulo very easily. So instead of normally you have to have Montgomery reduction or Barrett's algorithm to calculate the modulo of the result. But on this curve, we can do it just by doing some bit shifts and additions. So it's much faster, 2 or 3 times faster than if we had to use some other algorithm. The other point is it has an efficient endomorph. And what this means is that when we're doing a point multiplication on the curve, we can actually split this 1 point multiplication into 2 half-size multiplications. And this is actually faster, but also on the FPGA, we can do it in parallel. And so we use these 2 points to get speed up on the FPGA. This is just showing a top level of the engine that we designed. And so the main function was for taking in a message saying, here's a signature, ECDSA, and is it correct? So we will take in a message and we return the result. So we have some control logic. Internally, we're using a data path, which is of the native bit size, so FP of 256 bits. In order to calculate the inverse of a value, we use a binary GCD algorithm. So this is just doing adds and subtractions and bit shifts. And wherever I have an R here, it's just showing that we're using some storage or registers on the FPGA, which are all native size, so 256 bits. Once we do the inversion, we come in here and we have our endomorph decomposer, where we take our value that we're multiplying by, and we split it into 2 smaller ones. And you'll see here that we have some certain equations we need to calculate, and we have some storage as well. And this guy will require multiplication, subtraction, and addition. And these are all our interfaces that I talked about before. So we have our endomorph, which is then our 2 smaller multiplications of around 128 bits. And then we're doing point multiplications. So we do these in parallel. And this is the right to left algorithm where we're saying, okay, point double, point add, point double, depending on the binary value that we multiply by. And then we have what is a point add and what is a point double. So this is actually a bunch of equations. And throughout the design of the Verilog, what we've made is we've tried to make a very modular format for equations. So all of these blocks are quite similar in the fact that it's some equations, some memory, plus interfaces to what kind of arithmetic they need. And if we want to implement something different, we just add some equations or implement what equations we need. And when we design this block, we specify, okay, this equation requires this equation to be finished. but this equation can start without anything before it. So it allows us to exploit the parallelism of our equations without actually defining, okay, these two equations work in parallel, these two are in parallel. So it makes it much more robust and high performance. But yeah, so we have our point add and point doubles. We have 2 of these for each. And then we have our interfaces. And this is connected to our FP arithmetic, which is a shared block, which will pretty much help us calculate whatever comes on these. So this is the arithmetic block. You'll see here we have our arbiters, which I showed earlier, on the input and output, which is, it's actually one block where, this is adding the index, so marking the input, and then this is putting the output on the right block. For multiplication, we implemented a Karatsuba multiplier, and what this does is, on the FPGA we had to take 3 clock cycles, and it takes in a multiplication and it splits it up into 3 multiplications with a couple of additions and subtractions. And this was to reduce the usage on the FPGA, and it took 2 stages, so 6 clock cycles for us to do the 256-bit multiplication, which is 512 bits if we have A and B, right? Also, part of our ECDSA required us to have different kind of reductions. So actually, when we're calculating the endomorph, we just need a bit shift, so it's very simple. When we're calculating anything that's on the curve, we do it mod prime, and then this can take advantage of our very fast modular reduction algorithm. But if we're doing something in the setup for our ECDSA, we actually require mod m in, which is the group order. And because of this, we implemented Barrett's algorithm. And Barrett's algorithm, when you're doing a modular reduction, actually requires 2 more multiplications. So we kind of reuse the same multiply here. And this takes longer, but this allows us to get the result. And then addition and subtraction,
These are all in.
Sorry.
Sorry. These are all in FPGA, right?
Yeah. Yep.
Not in CPU, right?
No, everything is on the FPGA. So we made a block that does Barrett's on the FPGA, and this is just like a multiplexer on the FPGA. And the reason we didn't do Montgomery is because Montgomery also requires 2 multiplications, and we already have this multiplier, so it just made it simpler to keep it without having to do the Montgomery conversion. And then this is the adder. Yeah, sorry.
Yeah, thank you for explaining that.
Okay. Yeah, and so for the adder and subtractor, we have just 2 clock cycles. And what we did is we have one kind of pipeline where we do the addition or subtraction, and then one pipeline where we take an offset, right? And then on the output, we select which is the correct result. And this way we do our modular subtraction and addition. Yeah. So this is the results for the second block, the transparent transactions. So we found in the end that we only got 1.5x sped up. And this is possibly likely due to the fact that we have parallelism, but it's not a huge amount. And also the software library we're comparing it to is very highly optimized. So it's hard to kind of get an advantage over it. But you can see when we added the endomorphism, we doubled our performance. Even though the multiplier at the very basic level is just 1, because of our kind of equations and parallel operation, it can use kind of the idle clock cycles without really impacting the performance. And also, if this was important, you could implement multiple cores to get higher performance. But we just have 1. This was that was the transparent transactions, and now I wanted to talk about zk-SNARKs and what we did for those. This is kind of just like a basic introduction. So zk-SNARKs stands for Zero Knowledge Succinct Non-Interactive Argument of Knowledge. So what it means is that you're basically creating a proof that you know something, without revealing any knowledge of what you know. And so this is very important for privacy, right? Like you need to prove that you are able to spend some money, or you're able to sign some transaction, but you don't want to reveal, okay, who you're sending it to, or how much you're sending, or even who you are. And the non-interactive part means that there's no kind of back and forth. So it's just you provide this proof that anyone can verify is correct without actually getting the knowledge. And this picture kind of shows an example of, on our transparent transactions where we used the ECDSA, you can actually see you have a signature, which is our ECDSA, but you can see it's Alice, and we can see it's 2 Bitcoins, right? But if we're doing shielded transactions on Zcash, you actually don't know this. So you see a proof and you know it's correct, but you can't see who's sending or how much. So this is really the very high level of privacy. But the disadvantage is that instead of just doing point multiplications, now it's a little bit more complex. And there's different sides. So we have the proving side where we're creating the proof, and the verification side. And we decided more to focus on the verification side. And in the verification side, so every node, when it downloads the blockchain history, has to verify, right? What it's doing is point multiplications and pairings, which is kind of a bit more complex ECC. There are also FFTs that are done, but this is done on the proving side, so we haven't looked at this in this project. And this is just a slide showing for the Zcash blockchain. So in 2018, they had an upgrade to Sapling, which was the next the network upgrade, and this is where they had a huge number of kind of improvements. So originally, it was nearly a minute to approve one of these transactions, so it was quite slow. But with this upgrade, now it's down to just a couple of seconds, and verifying is even faster. And there's a bunch of different improvements that the engineers came up with. One of them was changing the proving system and also the curve. So you'll see now we're operating on this BLS 12381 curve. And the operations on this are the verification, the pairings, which I'll talk about, and also the multi-exponentiations, also for creating a proof. And so what we talked with the engineers, and what we decided is we wanted to add some FPGA acceleration to this curve, pretty much the BLS 12 curve, because a lot of arithmetic, a lot of the runtime is based on this guy. So pairings is another kind of complex operation we're doing on elliptic curves. And what we're doing basically is that we're having points on the elliptic curve. So we have 2 groups, for example, G1 and G2, and they'll be in different fields. So we have our prime field here, but now we have something which is called an extension field. And I have a slide to talk about this. But what we take is 2 points and we pair them, and we produce an element in a different group, which will be, for example, here in FP12. And this 12 means that the extension field, or our point, is much bigger now, 12 times bigger. So of course, all of the logic is a lot more complicated. So in addition to just doing point doubling and adding, we need now to do the Miller loop and final exponentiation algorithms on top of this. And now we're also dealing with towered arithmetic. So previously, for the transparent transactions, we could just stay in the FP. Now we actually have to do operations where we're doing FP12. And instead of saying, okay, FP12 is 12 times FP, it's actually a lot more efficient to have a towering, where we say, okay, FP12 is the same as 2 times FP6, which is 3 times FP2, which is 2 times FP. And this gets us some kind of efficiency in doing the algorithms, but it's another level of complexity. And then finally, we need to be able to implement addition, subtraction, multiplication, inversion, but also we have some new things, so forensic map, as well as exponentiation. I talked about towered arithmetic, and this kind of tower of extensions. So when we say, okay, we have a FP12 to the power of 12 point, and we're going to represent it by FP6 or 2 in FP, The big advantage is, for example, we can now do multiplication on an FP12 using some non-schoolbook method. So, for example, if we took the very basic schoolbook method where we do all of the cross products and then we add up all the results, and a single FP12 element would actually take 144 FP multiplications. But if we're using something like Karatsuba, where we split the multiplications into, log 2 multiplications plus some additions, we actually only need 54. So this is where the towering arithmetic kind of comes in and gives us the advantage. So in the FPGA, we've implemented this as well, using the towered FP12 arithmetic. And the way we've done it, again, is using equations where, for example, FP12 will have interfaces to FP6, and FP6 will have interfaces which go to FP2 and so on. And because of the way we're streaming our interfaces on the FPGA, we never have anything bigger than 1 or 2 of the base field. So for our BLS 12381 curve, we might have 762 bits, right? Because we kind of put our coefficients on top of each other. But for example, if we're doing a point inversion, we don't need this, so we just stream the point through. And these are the coefficients in the extension field. So for example, FP6 will have 5 coefficients, and each coefficient can be looked at as like an FP element. And when we're doing
question, sorry. Yeah, for the curve element, like the 381 bits, there's 3 bits of flags. Do you need to store that 3 bits of flags somewhere, or?
No. So on the FPGA, we can on the FPGA we can actually say, okay, the data bus is 381 bits, because we can program it. So we actually there's no kind of 3 bits of overhead. We specifically say 381. You'll see we actually make a coprocessor. So we actually, because we have to interface to a software memory region, we actually do add a few bits. But we use this for metadata. So I show this in a second.
Okay, thank you.
This is an example of when we have a point doubling, for example, on an extension field. On the FPGA, this is a System Verilog function which we use for verification. So we've detailed the algorithm we want to implement, and we can check this as our kind of golden result. But the FPGA will actually also implement very similar things. So it'll have equations, and each one of these is an equation. And we say, okay, once this equation is finished, then this one can go. And you'll see if we're operating on like the FP2 extension field, our multiplications just become FP2. And this lets us use the same kind of equations for different extension fields. And we can reuse a lot of the FPGA kind of logic. And so then just summing up what we need to do. So Zcash, they actually calculate the optimal 8 pairing. So when you talk about pairings on elliptic curves, there are different algorithms to get the similar kind of result. And the optimal 8 is right now kind of the fastest one. And so a lot of people using it. So this is the same one we implemented. In order to calculate this guy, we need to do two kind of high-level algorithms. And the Miller loop is the first one, which is we are doing point doubling, addition, and FP2. And we can reuse this to actually do point multiplication, so we don't need anything extra for that. And then we'd have addition, subtraction, squaring. And as a result, we're actually producing FP12 elements, but a lot of the coefficients are 0. And so because of this, we can kind of implement sparse multiplication. And so the result of this algorithm is an FP12 element, which then we take and do a final exponentiation. So we raise FP12 to the power of this, which is, takes quite a long time. And what it ends up being is inversions, exponentiations, parenthesis map, which is when we raise to the power of p, and then subtraction and multiplication. Okay, yeah, so for our pairings, this is the curve that Zcash uses, BLS 12381. It's 381-bit prime and has an embedding degree of 12. And it's kind of known as a pairing-friendly curve. And the reason for this is one of the parameters, the Z value, is a low Hamming weight, which this means the Miller loop is more efficient. So we don't need to do as many iterations of the Miller loop. K is the embedding degree, and this is the one that our final element is going to be put into the group. So we have FP12, which is this 12. So 12 is not too large. Security level is around 128 bits, and the prime modulus doesn't have anything special, so we need to come up with either Barrett's, Montgomery, or we actually use the kind of lookup table approach. And we have a Rust implementation we can compare to. What we decided to implement was a coprocessor. So this is all on the FPGA, but it's kind of like an acceleration processor that the software can talk to do operations on the curve. And so what we implemented was an instruction set, which was custom, as well as kind of custom data memory and instruction memory. And so because we need to map our data back into software memory so that software can access the processor, we did actually add 3 bits. So we add 3 bits to every 381 metadata. And this 3 bits is just in the RAM on the FPGA. So we just store this metadata. But when we're actually doing calculations, we don't have this information. And this metadata is used just to identify what kind of data is stored at this point location. So we have a single FP element, but it can actually be part of a FP12 or AF is fine. So this is our X and Y. JB is the Jacobian projective coordinates, X, Y, and Z. And then this is showing kind of the instructions that we implemented. So we have basic instructions that are for control, like jumping and copying. We have a send interrupt instruction. And what this does is let software can program the FPGA to say, okay, perform. We actually, for example, on the Groth 16 for zk-SNARKs, the verification requires 3 pairings, I think. And so what we can do is have the FPGA do 3 pairings back to back and then send us a result. And the send interrupt will tell the FPGA to send us some data. So we don't have to kind of poll for the result on the FPGA. And we then have like multiplication, adding, sub, inversion, and the software can just tell us, okay, data slot 0, do an inversion, and the FPGA will say, okay, do I have FP2, FP, or FP12? And it will automatically do the correct inversion. And then for the higher level functions, we have point multiplication, Miller loop, final exponentiation, and 8 pairing. So software can write a combination of different instructions or kind of program flow, and the FPGA will run it and send back a result. This is like a high-level block diagram. And so we have some interfaces coming in. So this is all on the FPGA, and the software is out here. We have software can access the memory regions of the processor using a kind of memory map. It's a little bit slower, so it's XE light, and it gets access to 4 bytes in one kind of clock cycle. But this gets mapped into our 381-bit architecture. And then we have an interrupt sender, which is sending messages back to software. And this uses XE4 protocol. And so here you could have like a DMA engine or something so that software doesn't have to continuously pull or continuously check if the FPGA has finished. And then we have our instruction decoder, and this will feed our instructions through to the pairing engine, which has our Miller loop, double, add, final exponentiation. And then these all have interfaces to the required kind of arithmetic that they need. And then down here we have a common block, which is implementing the shared towered arithmetic. and that can be FP12 or FP6 or whatever. And so our instructions were 8 bytes per slot, and so this is like a operation plus some pointers. And then data RAM is 48 bytes per slot, which is 381 bits plus 3 bits of metadata. And this is showing our towered arithmetic. So, for example, when we want to implement multiplication on FP12, we have our resource arbiter. We describe what is required, the equations, as well as some memory. And then we have interfaces to the lower levels. And then this will be towered on top of FP6, FP2. And then at the very final level, we have our FP multiplication. And then, for example, some of these have a resource arbiter so that we can share access, but for inversion, we don't have to share. So we can just connect our inputs and outputs directly to the blocks above us. And so for FP12 inversion, we also use the GCD algorithm. Addition and subtraction in towered arithmetic is very simple, so we don't need to do anything special. And also because we're streaming our interfaces, we also have, there's no difference between FP12 or FP. Basically, every clock cycle, we take the 2 coefficients that are on top of each other and do the subtraction. Yeah, and what we found in the end actually is that the multiplication was the biggest bottleneck. And originally we were doing it using Barrett's algorithm. And for 381 bits, we had to have three levels of the Karatsuba. So it was taking close to 30 clock cycles, which was quite slow. We changed the multiplier to be a higher performance. So this is just showing the architecture we used. So originally we used Karatsuba multiplier and Barrett's reduction algorithm for calculating the modulus. But this was taking close to 30 clock cycles, and we found that maybe 1/3 of the whole pairing operation was multiplications. So what we did is we replaced it with this kind of architecture where we have a parallel multiplier. So we have our input coming in, which is 2 381-bit inputs. And then on the FPGA, we actually have these DSPs, which can produce a single 26 times 17-bit multiplication. So we have all of these 345 happening in a single clock cycle, so all in parallel. And then we have a lot of cross products that we need to accumulate. So the next clock cycle, we do a carry save adder tree where we combine all of our cross products down into a result. And then on the next clock cycle, we actually have this like 700, 800-bit result, right, that we need to reduce down to 381-bit. So the way that we did it is we used lookup tables where every bit past 381 is actually the address of some memory that we pre-calculated. And depending on if there's a 1 or a 0, we know what the modulo reduction should be. So we take all of this, and then we have another level of carry save adder trees, adding all of these results, as well as propagating our carries. So I mentioned here we don't use a redundant form just because the architecture was based on not using one, but possibly using a redundant form for our inputs and outputs would help because we wouldn't have to propagate these carries. But once we're propagated, we have one more kind of stage of RAM reduction, and we can use the same RAM as before. And then what we end up with is something that's 382 bits. So then we have, in parallel, we do a couple of reductions and we pick the result which is correct, right? And then this is the 381. And in the end, this approach took 9 clock cycles, which is nearly 3 times speed up. So it uses more FPGA resources, but because we're not using them anyway, it makes sense to use. So these are the results we found from the coprocessor. And so we benchmarked it against the Rust code that Zcash uses on a 3.7 gigahertz CPU. And we're just about getting 3x improvement. You can see here the logic on the FPGA. Now we're using more, so it's a quarter of the lookup tables. The RAM is being used because we now have this multiplier using lookup tables and our DSPs. So we're not using, even though we're using everything in parallel, it's still not that many DSPs. And then this is kind of showing the performance that we got. So you'll see the FPGA throughput for something small like an FP inversion is actually slower than the CPU. But as we kind of move up our towered arithmetic, because we have more equations happening in parallel, the gap kind of closes. So you'll see here, even FP multiplication is faster on a CPU, even though we have 381 bits, mainly because our clock speed is, we run this at 200 megahertz compared to 3.7 gigahertz. But when you move up the chain and we go to FP12, now because we have so many things in parallel, you see we're actually faster than the CPU. And you can see for the different blocks, we have our 8 pairing, and again, we're around 3x improvement. And the final pairing result here is 3x. So we implemented this BLS, but we also, one of the goals with the project was to have it kind of accessible for the community. So everything's open source. And we also developed the flow and tested it on Amazon AWS instances. So it means anyone can pretty much take the code and build it, or they can take a public image, which we have in the user guide, and test it. And this is just showing an example. So we run the test program. It reads the FPGA. It says, "Hey, what's enabled?" So in this one, we have the SECP and we have the BLS, and then it runs some tests. So it sends a signature to verify our result is 0, which means it's correct. And then we test the coprocessor, and we just do some basic memory reads and writes. We check that it's okay, and then we get our result back. So this is the result from a pairing where we have our FP12 pretty much coming back from the FPGA, and you can see it's passing. So this is kind of the end of the Zcash portion, and I have some slides now just on kind of concluding and also VDFs, because they're kind of interesting. Yeah.
Yeah.
Okay.
Yeah, please.
Okay. So yeah, so I just have a few slides on VDFs because they're kind of interesting as a FPGA acceleration target, and also for kind of blockchain technology. They're like an upcoming thing that you might see more often. So a VDF is a verifiable delay function, and it's basically something that takes a quantity of time to work through that can't be parallelized, but it can be verified very quickly. So the good points for FPGA acceleration here is that memory is not really the bottleneck. It's a custom data path. So it's, for example, you might be doing 1024-bit squarings, and you can implement this as 1024 bits on an FPGA, whereas on a CPU you need to implement 64 bits. There's not a lot of communication between the FPGA and software, so usually it's a lot of internal number crunching, a lot of internal kind of algorithms. And so if you compare this to a CPU, you can get some good speed up. So as an example, there was a MIT time capsule problem back in 1999 where they wanted you to calculate 80 trillion repeated squarings. And they estimated it would take 30 years. But then with some CPU algorithm kind of enhancements, someone was able to finish it in 3 years. And actually at the same time, a group implemented this on the FPGA, and it was done in just about 2 months. So you can see here just comparing, 10 to 20x improvement for this kind of VDF is achievable. And then the other point is that compared to ASICs, it'll be slower, so maybe 10x slower, but it won't be 100x. And this is important for what I'll show on the next slide. But the points for this is that due to the fact that it can't be easily parallelized, so ASIC doesn't really have a big advantage over FPGA. The advantage is going to be now that we have no programmability, we have a smaller delay, and we have a faster clock. But there's no kind of parallel advantage that you can use to make ASICs really fast. So this is good for proving proof of history or guaranteeing some bound of runtime, because you can say, okay, give me the result of this VDF, and it kind of verifies that you took so long to do something. So as an example is randomness, right, on the blockchain in Ethereum 2.0. So one of the kind of use cases is that it would be really good to have this kind of random data source on the blockchain. And also, if you're moving to a proof of stake system instead of proof of work, you need some way to randomly pick the winner out of some submissions for the block to be added and to get the reward. So RANDAO is one of these schemes that can do this. And the way it works is that every participant in the system will submit secretly a small number that they randomly produce. And then there's one round of this. Then after that, they reveal the number, and then the blockchain will generate the random number by combining everyone's. So this way, it's combining multiple sources of kind of randomness. But the problem is that if you have someone who can't be trusted, who's trying to possibly manipulate the random value, something they can do is they can wait and see the final result of everyone else's random number, and then they can decide to purposely withhold their number. And this can possibly have an impact on the random result. And maybe it's very small, but then they can use this to possibly affect something and have a big outcome. So you can solve this with VDFs by saying, okay, there's a maximum time a participant has after they submit their random number before actually you have the random number generated. And so you can use a VDF for this. So for example, the random number you generate is not the XOR of everyone's inputs, but it's actually the result of a VDF, which might take 100 minutes. And if you do this, then you can guarantee that, okay, if I'm limiting everyone 5 minutes to submit a random value, you can't wait 100 minutes to see the result before deciding, because by that time I've cut you off. And so this is the main idea, is to have a reliable bound kind of on the runtime, even if you have someone who has an ASIC, because maybe they'll be 10 times faster, but they won't be 100 times. Yeah, so this is kind of an interesting application. Sorry?
Excuse me, may I ask a question about you said that ASICs might be 10x faster than FPGA,
yep.
Right?
Yep.
How is it estimated or calculated? Just a little bit curious.
So you can kind of think of an FPGA and an ASIC as the same thing, in the sense that when you design an ASIC, you write some hardware description language, and then you fabricate it. But on an FPGA, you're fabricating it to some programmable logic. So the FPGA, the reason the FPGA is slower, the clock speed, is because you have the kind of programmability, right? You have all the multiplexers and this kind of thing. So for example, if I go back to the top, on an FPGA, you have these kind of switching matrices, right? On an ASIC, you don't have this. Yeah. So this is adding to the delay, which is making your clock speed slower. On an ASIC, you don't have this. So you can pretty much say, okay, if the ASIC is going to be the same design, so I can guarantee there's no kind of like parallelism that you can implement on the ASIC that the FPGA can't. The ASIC's advantage is only going to be that it doesn't have the switching, right? And so you might get a clock speed coming up to 3 gigahertz, which is 10x. But it's never going to be it's never going to be 30 gigahertz. So
yeah. See. Thank you.
Yeah. So this way you can kind of show this. Yeah, so this is just kind of concluding the different things I've talked about. So we had a project where we wanted to implement FPGA acceleration on the Zcash blockchain. We did 3 big things. First was Equihash, and we got a good speed up, 207 times, and mainly because of the parallelism and the hashing. Then we looked at transparent transactions, which was Secp256k1, where we got a 1.5x. Here it kind of seemed that there was less opportunity for parallelism. Our 256-bit data pipeline is not so far away from a 64-bit CPU. And if you look at the clock speed, we're already 15x disadvantaged. So when you put something on an FPGA, you really need to, get parallelism or get really custom logic to overcome this. And so something might be multiple cores on an FPGA, but we didn't do this. Then we looked at zk-SNARKs, and we decided to implement the BLS12 coprocessor. This can do pairing, it can do other kind of zk-SNARKs multiplications. So the pairing operation has more parallelism, it has a higher pipeline to give us an advantage. And we also were able to implement a kind of high performance multiplier. So in total on the FPGA, if we put everything on, we're using around half of the LUTs, 20% DSPs and 30% of the RAM. So this has all been released open source on GitHub, and the idea has been to kind of make it very modular and easy to use so that it can be ported to other curves. For example, if Ethereum is using the BN256 curve for zk-SNARKs, this could be used for that, or for other projects using elliptic curves. And just finally, like future direction, zk-SNARKs. So they also use FFTs for creating proofs, which would be a good candidate for FP acceleration. Although in our use case, we just did pairings and multi-exponentiations for greater speedups. Other curves, so blockchain technology is kind of advancing really fast. So Zcash also recently came out with Halo, and Bitcoin have bulletproofs, which are for the very zk-SNARK kind of technology, very private transactions. They don't use pairings, but they do a lot of ECC point multiplications. So there's still kind of some opportunity for acceleration. And the other thing is to be like, we could try using architectures like redundant form or RNS on the FPGA to try and get a faster clock speed. Because we implemented 200 megahertz for this project, but maybe if you implement kind of redundant form, we could get 300 or 400, which is 2x improvement. Yeah, and they didn't find any acknowledgement. Thank the Zcash Foundation for supporting this work, and all of the feedback and guidance I got from the engineers while I was doing it. Yeah, thanks. Does anyone have any questions or comments?
Thank you, Ben. And I saw a question in the chat box, and it's like many slides ago, and
okay,
because like a question like how to choose FPGA for if he needs more than 12C times 25 independent head on the board.
If you need more than
yeah.
What was the resource you were talking about? Sorry. Oh, the RAM.
12 RAM or it's right. 12C times 25.
Do you know what slide number this is for?
I'm not sure right now. It's near you see the message, the chat message. 12. Okay.
Yes, I don't totally.
Step back and
yeah, so I I don't totally understand what is 1 to 12c times 25.
Never mind.
Okay, maybe yeah. If anyone has questions later, they can just email me, or we can talk in the the Zcash community chat. Yeah.
I have a few questions. Sorry, I arrived very late.
Okay.
One of my questions is, what is the rationale behind the specific license that you chose? Is that something that you went ahead with, or did the Zcash make a recommendation?
So originally, yeah, it was pretty much Zcash's recommendation to do the GPL3. It was going to be MIT or GPL, and I think they just preferred GPL. Okay, great.
And do you think they would be open to the idea of relicensing or dual licensing?
Yeah, I mean, I think they wanted this to be kind of used by more people. So if if that helps out, then yeah, I'm sure.
I guess another question I have is, so one of the things I'd like to see at one point is to have some sort of SNARK prover ASIC. And so if I understand correctly, the BLS12381 multi-exponentiations, the speed up is relatively small, let's say. Is it on the order of 2 to 3x? Is that right?
Yeah, that's right. So for this one, we kind of came at it as looking at the, we wanted to accelerate the verifications first rather than the proving.
Right.
So we looked at pairing. But I think if you wanted to actually speed up, so this processor can do the multi-exponentiations, but it kind of does them in serial. It doesn't parallelize it. So I think you could go back and look at that and then kind of change the architecture to get a better speed up on that. It just wasn't the kind of focus for this one.
Okay, so there's a single core right now.
Yeah.
And that provides us more speed up. And how many cores can you fit in
so I mean, it all depend on the curve. So this one was 381, and we ended up with, so it's like 25% of the FPGA already. A lot of this is due to the multiplier that we used, and that gets shared by everyone because it's fully pipelined. So you can get, it can take a new result every clock cycle. So I think you could probably fit, like just an estimate, maybe 4 or 5 of these cores. Without having too much trouble.
Okay.
Yeah.
And that's the AWS F1 FPGA.
Yep.
Okay. Yeah. Great. I mean, today is I think the final day for the release of the multipliers from the FPGA VDF competition. So
yeah,
you may be able to use even better multipliers.
Yeah. So actually, originally I was looking at that, but then kind of didn't have time to really have a good go. But I was able kind of to take one of the approach, the idea of that paper, but using the lookup table and apply it here. But I think like using redundant form or something would be even better. And I guess that's what will come out of the VDF competition, right?
Yeah, I mean, in a way, the VDF competition is not really appropriate for what you're trying to do, because the VDF competition is trying to minimize latency, whereas I imagine you want to, optimize for bandwidth and area.
Yeah.
So I'm quite optimistic that you can get much better performance than this.
Yeah.
So, in terms of future plans, are you still working on this project? Do you still have funding?
So it was kind of until the middle of October. So it's kind of winding down now, and most of the work is just documentation or kind of support rather than developing new stuff. Yeah. So we started in around January. So kind of this is the end of the 10 months.
Okay, great. And do you have any like future plans? Like,
so I in October I have to go back. So I'm currently living in Taiwan because of the non-compete. but in October I'll go back to New York and start working in a full-time job there in FPGA. And it's a Jane Street. It's like a HFT company, but
Okay.
I'm pretty interested in this kind of stuff as well. And so I think I've been talking to some Barry Whitehead's been helping me. We've been putting together actually a kind of a proposal to do a zk-SNARK prover for Ethereum on the FPGA. So I'm not sure if that will come through or not, but it might be something as like a side project that I'd like to have a go at. And I think a lot of this can be reused for it.
Oh, that would be great. Yeah, I need to talk to Barry about that.
Yeah.
And the HFT stuff, I guess, is very relevant with the VDF because I couldn't think of many industry applications where you need low latency, but
yeah, exactly. Yeah.
HFT is one of them.
Yeah, exactly.
Okay, fantastic. Thank you, Ben.
Yeah, no problem. Thanks.
Sorry, I got a question from the Joseph Zhang, and he asked about it's actually the X25 integrated circuit bus.
Okay. So I think is this kind of this is like the input. It's kind of related to the input and output of the FPGA. I2C, like the serial kind of protocol. So I haven't. I think that's kind of what is right when you have the input and output from the actual FPGA. And for this project we didn't have to do any of that. We just did USB or PCIe. Crypto IC 255.
I see. Yeah.
Yeah, I'm not too familiar. Maybe afterwards I can like look up what it is and talk about this offline.
Yeah. I think if Joseph, you are interested, let me organize another offline discussion for that. So, any other questions? Okay. So, yeah, I think that's all. Thank you, Ben, for presenting this wonderful talk. And
yeah, no problem. Thank you for letting me.
I hope you're welcome.
Yeah.
So yeah, see you somewhere in the future.
All right. Thank you.
Yeah, and thank you all for participating. Bye bye.